Assalamu alaikum. Bismillahirrahmanirrahim. Comes our second and very important topic, that is about hydrogen bonding. The crucial thing is that there is hydrogen. Hydrogen is one of the smallest. Hydrogen is the smallest atom of the periodic table, and it can approach to the other atom very closely, and due to which if it forms a sigma bond, that would be a very strong sigma bond because of small size of atom. In fact, it has only one s electron and only one proton, so one shell is there, and that is to take part, this electron is to take part in the process of bond formation. Due to this, it can approach to other molecules as well because of its small size. That is something crucial. Hydrogen bond is attraction, that here I try to highlight it. Sorry. A hydrogen bond is the attraction between the lone pair of an electronegative atom and hydrogen atom that is bonded to either nitrogen, oxygen, or fluorine. Very electronegative elements. When hydrogen is covalently bonded to fluorine, oxygen, or nitrogen, electronegativity of fluorine is, you know, that 4.4, that is the highest, oxygen 3.5, nitrogen 3. These elements are very electronegative elements. When hydrogen is bonded to these elements, it becomes sufficiently positively charged. Now hydrogen bonded to these elements covalently, having sufficiently positive charge, can approach to the lone pair of another atom which may be present in the same molecule or which may be present in some other molecule, and can interact with the lone pair of that other atom. So it's this attraction between the lone pair of an atom, electronegative atom, and partially positively charged hydrogen atom that is bonded to electronegative atom is called hydrogen bonding. Hydrogen bonding is the strongest intermolecular attractive force. Dipole forces are weaker than hydrogen bonding, and London forces are generally even weaker than dipole forces. Exceptions are always there. Hydrogen bonds are not covalent bonds. They are sufficiently strong interactions, but they are weaker than covalent bonds. So we move on to our next. Here beautifully explained hydrogen bonding. You can find here purple color. That here is with purple color, with blue color I have highlighted, and purple color dashes you are watching, and hydrogen bonds words hydrogen and bonds are written in the purple color. So lone pair is on electronegative oxygen atom. On the other end, this hydrogen is bonded with electronegative oxygen atom. Due to its bond with oxygen that is very much electronegative, second most electronegative element of the periodic table is oxygen. This hydrogen acquires partial positive charge. I explained this. This hydrogen acquires partial positive charge, and you know that this oxygen of course is partially negatively charged. Now this partially positively charged oxygen forms hydrogen bonds with this oxygen. Partially positively charged hydrogen that is bonded with electronegative oxygen interact with the lone pair of other electronegative atom of other molecule. Same hydrogen bonding you observe here. Here this hydrogen is and this oxygen is. Same hydrogen bonding you are observing here. Same hydrogen bonding you are observing here. So in all these cases, you know that central water molecule, there are two hydrogen which are partially positively charged. They are forming hydrogen bonds with lone pairs of oxygen, and at the same time there are two lone pairs on oxygen atoms which provide sites for hydrogen bonds to other hydrogen atoms of other molecules. So two hydrogens of central water molecule, two hydrogen bonds, and two lone pairs provide sites for two hydrogen bonding. So this is beautiful explanation of hydrogen bonding in case of water molecule. If you put ammonia in water, then of course similarly as for example this hydrogen is, so in case of ammonia, in case of at the place of oxygen there would be nitrogen, and hydrogen will form in this hydrogen bond in the same manner. And here in case instead of oxygen there would be in ammonia there would be one lone pair and nitrogen there. So we move on to our next slide. Applications of hydrogen bonding. First of all, thermodynamic properties have been discussed, and among thermo means heat, dynamic motions, properties which change by changing temperature, they come under the topic thermodynamic properties. And in this slide I have chosen such a way, such a slide because in your 2020 edition group number are currently written group 14 for example, and in your textbook in this topic group 4A is written. In your old versions of book you find group 4A, but in new you can find both 4A as well as group 14. Group 14 consists of, it is also called carbon family, consists of carbon, silicon, germanium, tin and lead. Carbon is present, here is period, number of period, here are boiling points given, temperature is given, and there may be different boiling points of different substances. So we start with group 4A, which I have highlighted with blue color. Carbon is the first element present in second period. In third period silicon is present. In fourth period germanium is present. In fifth period tin is present. So when these elements combine with hydrogen they form hydrides. Binary compounds of hydrogen are called hydrides. There are two types of elements should be there. One is hydrogen and one some other element. All these are hydrides of group 4A are non-polar. So they have only London dispersion forces. As I have previously told you that London dispersion forces increase as we move down the group from top to bottom. It's due to increase in the number of electrons, number of shells. Polarizability increases, electron cloud increases, and London forces become stronger, and as a result boiling points become increased in value. So all hydrides of group 4A, which I have shown with green color in the graph, they have London dispersion forces and their boiling points increase as we move from top to bottom in a group. Next, further it can be explained that among the elements of second period and groups of 5th, 6th and 7th, you find that in case of topmost elements, for example in case of group 5A here is ammonia, in case of this one is ammonia, in case of group 6A here is hydride of water, oxygen, that is water, and in case of group 7A that is HF. So these are top elements, and you find that they have highest boiling points among their groups. The reason is this: all these have hydrogen bonding. Due to hydrogen bonding they have high boiling points. As we move to next period or down in the group, for example in case of all these fifth, in case of all these groups 5th, 6th, 7th, in case of 5th after nitrogen you find phosphorus, so its hydride is here, that is phosphine. In case of I highlight rather than writing by pen. In case of HCl after fluorine, in case of halogens after fluorine there is chlorine, here is HCl. And in case of water, in case of group 6A after oxygen is sulfur. So H2S, H2O, these are compounds which are lacking hydrogen bonding due to small electronegativity difference between hydrogen and sulfur, hydrogen and chlorine, and hydrogen and phosphorus. Either have dipole-dipole forces or London dispersion forces, which are weaker. As a result they have low boiling points as compared to their respective top elements. Similarly, from now onward London forces become prominent. When we go to third to fourth period, you find that on descending, on moving from top to bottom. For example, after oxygen is sulfur and after sulfur is selenium, you find some boiling point higher. Reason is that now size of selenium is bigger than that of sulfur and London forces become stronger here. Same is the case with almost all the elements. In case of element which are under this. In case of HCl or HBr, there is slight difference in their boiling point. Reason is that HCl has dipole-dipole forces, whereas HBr has weaker dipole-dipole forces and stronger London forces. In case of HCl, weaker London forces are there. So HCl has stronger dipole-dipole forces, weaker London forces, whereas HBr has weaker dipole-dipole forces, stronger London forces. So as a result of which there is slight difference in their boiling point. Okay, next is something else. If you discuss only electronegativity difference on one bond and thereupon strength of hydrogen bonding, then of course HF should have stronger hydrogen bonding than OH. But in case of water molecule, you have two hydrogen atoms which are available in each water molecule for hydrogen bond formation to oxygen of another atom which has two lone pairs, and due to these two lone pairs, two hydrogens can form hydrogen bonds, and due to those hydrogen bonds, more number of hydrogen bonds, water has higher boiling point as compared to the HF. So that's why water has higher boiling point than these things have been discussed in our next slide. We'll move on to next slide. All these things have been discussed here. Group 4A is lower boiling points. Reason is I have explained everything. You are to read this through your textbook and also from this paragraph. You are to number 1, 2, 3, 4, all these things. We move on to our next. Solubility of hydrogen bonded molecules. You know that like dissolves like. If you have some polar molecule, it would have positive and negative end. So due to polarity, it can attract other molecules. And in case of water, there is possibility that anything that can form hydrogen bond with water molecules would be soluble in water. Similarly, hydrogen bonded molecules like methanol, ethanol, carboxylic acid, they form hydrogen bond among themselves. They can form hydrogen bond with water molecule, and due to which they are soluble there. So like dissolve likes and polar substances are soluble in water. Cleansing action. Fats and oils are main part of stains that are at our clothes. Their molecules can, whereas soaps and detergents are alkyl or aryl benzene sulfonate. Detergents are aryl or alkyl benzene sulfonates, whereas soap is sodium salt of long chain fatty acids or carboxylic acid. So long chain fatty acid, carboxylic acid, they have polar and non-polar ends. Alkyl portion, hydrocarbon portion is non-polar one, whereas carboxylic acid portion is polar one. So non-polar is dissolved in, or non-polar becomes part of strains, and polar becomes part of water, due to which when we shake water, it moves away strains from our clothes. So cleansing action is also due to attraction between water and polar and soap molecule. Next is hydrogen bonding in paints and dyes. You know that wood is of cellulose, and cellulose is glucose which have OH groups. Paints and dyes have adhesive action to hydrogen bonding. Similarly, hydrogen bonding also makes glue and honey stick substance. Clothing. We use cotton, silk or synthetic fibers for clothing. Hydrogen bonding is of great importance in thread making materials. This hydrogen bonding is responsible in the rigidity and tensile strength, how much it can be bent without breaking. That is tensile strength. So clothes, you know that either of protein like things, amides there, and or some carbohydrates there. So due to which hydrogen bonding can be possible there. Food materials, you know that carbohydrates are carbohydrates, you may know that polyhydroxyaldehydes are ketones. They have polar groups. Hydroxyl group are there. They can be available for hydrogen bonding. Glucose, fructose, sucrose, each of them contains OH group, which is responsible for hydrogen bonding in there. Hydrogen bonding in biological molecule. This is something more important for medical related students, although it is knowledge and equally important for every student, but in their field it is more applicable. So structure of proteins, you know that they are formed from amides, and their primary structure is sequence of amino acids. Secondary structure of protein may be alpha helical structure or beta pleated shape. These alpha helical structures of the secondary structures of proteins are beta plated structure. They are due to the hydrogen bonding. Similarly, you can find hydrogen bonding in hereditary materials. DNA is double helical structure. These strands, double strand structure, and these strands are linked together through hydrogen bonds. So here I have tried to explain this. In case of DNA, you have DNA, you know that polymer is of nucleotides, and nucleotides have, among other things, nitrogenous bases, phosphatic groups, and other things are there. But main thing is that is for our interest, that is hydrogen bonding. These are complementary nitrogenous bases. Guanine and cytosine, you are watching at top, it forms 3 hydrogen bonds here. You know, 1, 2, and 3. It forms 3 hydrogen bonds. At the same, cytosine is one strand and guanine is another strand. They are complement. They are in front of each other, as a result of which hydrogen bonding is developing here. And due to these hydrogen bonds, double-stranded DNA molecules exist. Similarly, thymine, you can find here, adenine, they can form. They are also you may call complementary nitrogenous bases, and here oxygen is with this hydrogen forming a covalent bond. Hydrogen of this nitrogen is forming this lone pair of this hydrogen bond. So due to these hydrogen bonds, cytosine and guanine 3 hydrogen bonds, and thymine and adenine 2 hydrogen bonds, double-stranded DNA structure is possible. And how is that double-stranded DNA structure look like? You may watch this on our next slide. This one is there. Double-stranded structure is, and these are hydrogen bonds here, which I have just explained. So we move on to our next slide. Here is the secondary protein structure. That is on the right hand side. You are watching alpha helical structure. This one is alpha helical structure. Within the same single strand, spiral like structures, and this spiral-like structure, and this spiral-like structure is due to hydrogen bonding. And at the same time, you find here, that is left hand side, beta pleated shape. This one, in beta pleated shape, you have nitrogen here bonded covalently with hydrogen, and at the other hand, carbonyl group oxygen. So this oxygen lone pair and this hydrogen forms hydrogen bond. Similarly, here is hydrogen bond, here is hydrogen bond, here is hydrogen bond. So due to these hydrogen bonds, beta pleated secondary structure of protein is possible. And on the other hand, due to hydrogen bond, alpha helical structure is possible. So further explained here is alpha helical structure of protein. Red you consider oxygen, and white you consider hydrogen. So hydrogen bonded with blue nitrogen, and on the other hand with oxygen through hydrogen bond. So spiral like structure due to hydrogen bonding is explained in this diagram.